Hello everybody. The last video we talked about buck converters and the basic circuit for buck converters, and we saw the waveforms and how we control the output of the circuit, and we actually manually switched the circuit to demonstrate the principle of work for the circuit. Today we will use the same circuit, but we will do automatic switching for it. We will remove the switch and we will use a switching element. Actually, in the electronic circuits, the most famous method for switching is using a transistor. The transistor can be a BJT or a MOSFET. We will use a MOSFET in our circuit today, and we actually will use a P MOSFET to switch this circuit on and off, and we will use it on the high side of the circuit, not the low side. Now, why did we choose MOSFET? We can choose another element, but MOSFETs are really easy to use, and they have very good characteristics for high switching. So we will use a P MOSFET. We actually can use an N-channel MOSFET, but we need a more complex circuitry for this. I will explain this in another video, but for now we will just use a P-channel MOSFET for switching. So now I will remove this switch and I will replace it with P-channel MOSFET. And this MOSFET, you can see that the source is connected to the 12-volt power. This node here is the 12-volt power, the 12-volt from the battery. So it is connected to the source, and the drain is connected to the inductor and to the circuit. And we will drive the gate of this transistor to switch the transistor on and off. Now, to drive a P MOSFET, you have to make its gate lower than the source voltage. So to make this P MOSFET work, or to take it to the on state, you have to make the gate voltage less than the source voltage. So to do this, it is simple. You can see that the source is at 12 volt. So just taking the gate to 0 will switch the P MOSFET on, and if we put a 12 volt on the gate, it will switch off. So simply I will use a BJT NPN transistor. This NPN transistor will be connected to our pulse width modulated signal, and this signal we will generate it from maybe Arduino, or maybe a big microcontroller, or maybe a function generator if you have it in your lab. We will not go into details how we can generate this signal now. We will do it in the next video. But for now, we will just switch this NPN transistor using a pulse width modulated signal, and this signal can be a 5-volt signal. You can take it from a microcontroller. It has a duty cycle, and we will control this duty cycle, and it also has a frequency, and we will change this frequency. So after using this NPN transistor to make it do the switching for the PMOS, we will connect its collector. We will pull up its collector to 12 volt by 1 kilo ohm resistance, and we will directly connect the gate of the P MOSFET to the collector of our NPN transistor. So you will see now easily that when the signal is on, the collector will be shorted to the ground, and the voltage at the gate will be 0. So the MOSFET will turn on in this case. But if we in the other cycle of the pulse width modulated signal, when the signal is 0 at the base of this NPN transistor, then it will be off and it will just go from the circuit, and you will see that the gate is at the same voltage as the source, which means that this P MOSFET will be turned off. So we achieved what we wanted now, and the switching can be easily seen working. So now let's see. I'm using an oscilloscope now. If you see here, I'm using an oscilloscope to see the waveforms of this circuit. So let's see now how we can work with this circuit, and let's see the waveforms. You'll see that the circuit will operate. If you see this waveform now, and to just make it to give a waveform that makes sense, I will use just 20 Henry, which is not realistic, but we will use it anyway to just demonstrate. And I will use 20 Hertz frequency, or let's make it 200 Hertz frequency, with a duty cycle of maybe 40-45, and let's see how this circuit works. Actually, you will see that at this frequency 200 Hz, the circuit is working perfectly. There is a ripple on the output voltage. You see the output voltage in red now. I will take it to ground, so you can see now this is the ground, and this is our output voltage. It is 2.5 division, and there is 2 volt per division, so we are at 5 volt, as this DC voltmeter shows here. So we achieved what we wanted by switching the circuit at 200 Hertz. But actually there is a big drawback for this switching frequency, because when you are switching at low frequencies you need a very big inductor. 20 Henry is not realistic, so we want to switch at higher frequencies so that we will make the inductor and the component sizing smaller for to reduce the cost of manufacturing, for example. So to reduce the size of this inductor, we need to switch at a higher frequency. So let's say that we want to switch at a frequency of 1 kilohertz. Now I will use 1 kilohertz frequency, which means that we switch this switch on and off 1000 times every second. So I will use 1 kilohertz, and this inductor will go will be just only 100 millihenry this time, because when we increase the frequency we actually decrease the size of the inductor. It is a inversely proportional relationship between the inductor size and the switching frequency. So I'm using 10 microfarad capacitor, and now we will switch the circuit on and see how it works. Now you can see that we got our circuit working. It is working now. You can see the waveform of the inductor in the blue. This waveform is actually the drain of the MOSFET. So you can see how this inductor is switching now, and also you can see that our output voltage has rebel, but now you can see that it is not 5 volt, it is 7.5 volts actually. So to adjust the voltage level of our output voltage, we will reduce the duty cycle of our signal. Let's make it 30%. The duty cycle is the on time divided by the off time. So, and it is related to the output voltage in the buck converters. It is the output voltage is actually the input voltage multiplied by the duty ratio if the inductor is working at a continuous mode. So let's make it 30%, and let's see, it is now 6 volts, you see. So let's make it maybe 20% will be good. Now you see that our voltage is approximately 5 volts and the circuit is working as we wanted. We are switching now at 1000 kilohertz, 1 kilohertz, which is 1000 hertz. Okay, now we can increase the frequency more and more. It is better for economical for the cost of the circuit. If you want to build it and manufacture it, it is better to switch at higher frequencies, so your components will be smaller in size. So I will use now, I will make it 10 kilohertz switching. So let's make it 10 kilohertz, and at the duty cycle, okay, 20. And this inductor will be now smaller, let's say 30 millihenry. And let's see what we got. Now we got our circuit working. So now we have a 30 millihenry inductor, and we have switching frequency of 10 kilohertz, and we will see now the circuit. You will see that the circuit is working and the output voltage is 6 volts, so we have to reduce the duty cycle of the pulse width modulated signal to get 5 volts. So let's reduce it to 15. Okay, so you will see now that we have a 5 volt output, and there is some ripple on the output, a small ripple. But you will notice now that the switching of the MOSFET is not natural now. There is no time for the inductor to switch on and off, and there is a problem actually for the MOSFET itself, because some MOSFETs will not switch at high frequencies. You have to buy a MOSFET that is designed for switching at high frequencies. So let's say now that we want to switch at 30 kilohertz frequency. This switching frequency you can get from Arduino for the pulse width modulated signals, and let's say that we are using 30 kilohertz now, and for 30 kilohertz you maybe want to use a 20 millihenry inductor, and let's see. You'll see now that the MOSFET itself is not working correctly, and the output voltage is 10 now, and it is getting bad for the MOSFET, because this MOSFET is not able to switch at higher frequencies. So to solve this problem, we will replace this MOSFET with another MOSFET which is able to switch at higher frequencies. Let's see that this IRF 4905, we will remove it from the circuit, and we will use actually 2SJ56 MOSFET, a P channel MOSFET, and it is ultra fast switching MOSFET. Now I have to mirror this because I want to make the source at the power supply at 12 volts and the drain connected to the inductor. Now we will use this MOSFET for 30 kilohertz switching, and we will see that it will work very good in this circumstances. So let's switch it on, and you will see that now the MOSFET is turning on and off normally. So you will see that the voltage now at the output is 2 volts. So we need to modify the duty cycle. In this case, let's say we want to make it 45. So 45, 20 millihenry inductor and 30 kilohertz switching, and now you will see that we have 5.75 volt. Let's make it 40% duty cycle, and now you will see that we are getting 5 volts at the output, and the switching frequency is 30 kilohertz, and this circuit is working very good now with our new MOSFET. So what we learned in this video is that choosing your components must be realistic. You must take into account the sizing of the components. You cannot use a 10 Henry or 20 Henry inductor. It's not realistic. So you have to use smaller inductors, but to use smaller inductors you have to switch in higher frequencies. So using frequencies of 20 kilohertz, 30 kilohertz, maybe 60 kilohertz will make it easier for you to build your circuit. You also have to choose your MOSFET, because your MOSFET has to be ultra fast or maybe just fast MOSFET. Some MOSFETs will not switch as fast as the circuit needs, so you have to replace them and choose a very good MOSFET for this circuit. Now in the next video we will talk about how to connect this circuit with an Arduino. So we will generate the pulse width modulated signal from our Arduino, and we will also provide a feedback path from the output voltage to the Arduino, so it will sense the output voltage and it will adjust the duty cycle of the pulse width modulated signal to exactly give 5 volts in case of using bigger loads, and in case of voltage drops, the Arduino should adjust the duty cycle of its signal and also adjust the output voltage, so it will be a closed loop system. Thank you for watching, and please like and subscribe, and the most important is to comment so we can see your ideas for improvements. Thank you again, and let's see you in the next video.